So welcome back students again. Today we are going to start a new topic called the theory of congruences. And I'm sure that you might have learned something about this also. And one more thing I would like to update. Yesterday we were talking about whether there are infinitely number of Marcini primes and Fermat primes or not. So this was actually I searched a lot, but until 2021, it was claimed that were only a few Fermat primes and Mersenne primes. But one thing you can see when you writing Fermat primes, Fermat numbers and Mersenne numbers, okay, and you know that any two Fermat number or a Mersenne number, they are relatively prime. That is okay. If you are taking any distinct pair, so greatest common divisor of M, N, and M, R something. So they are relatively prime. And okay. And they are until now there is no evidence or there is no proof that they are infinite in numbers. Okay. So this is the update I wanted to give you. One more thing, that since fundamental theorem of arithmetic says that every natural number greater than 1 can be written as the product of infinitely many primes. And since they are a natural number, of course, so there will be infinitely many primes to represent them. Thing is that, okay. And no more update until now in this direction is there about their finiteness or infiniteness of Mersenne and Fermat prime. Okay, so let us go back. So theory of congruences, actually this is another way of dividing the numbers, okay? And this is based on what we say that based on the remainder when we divide some integer by another integer. And this foundation of this was laid down by Carl Friedrich Gauss, and from the beginning of his childhood he was a very bright student. In fact, before going to class he was very intelligent. It is said that at the age of 3, he was able to find out some error in payroll in his father's salary. So at the age of 5, when he went to school, so in that his teacher said that there is nothing to teach him. We don't have anything to teach him because he already knows so many things. And later, when he was he went for his first class of arithmetic. So he was at that time in the very first class answering to some question. He gave a way to compute the sum of n natural numbers. In fact, in particular, he gave how to sum the numbers 1 to 100. So 1, 2, 3 like this. One can write. Okay. This is the based on the book in number theory or somewhere else. I'm telling you. Okay. So what he made the pair 99 here and then a 98 here and 97 here like this. So as such, so total this makes 100 and then here also 100 like this. And here 15 and 49 here. No, 50 and 50 here. No, yes, 50 and 50 here. So it makes also 100. I think I'm doing something. I think here 97, 3, and it will go For example, it will go 49, then there will be 51, okay, and there, okay, 49 up to 51, it will be up to 49 and 51, it will be. Oh, sorry. So like this, there will be 50 pairs. There will be 50 pairs, and if you sum them, you will be getting like this. You see, okay. I think 100. Oh no, 100 plus one, like this. He was making, okay. It was making 100 plus 1, and so it is 101, and 99 plus 2, 101, and 98 plus 3, 101, and 50, 51, 101. Okay, so there are 50 pairs. So it makes what? It makes that 50 times of 101. So it is going to give us 50, 50. So this gave that technique to derive the sum, and another technique to derive the sum of the numbers 1, 2, 3 up to n. And the way he found the sum from of number from 1 to 100, the similar technique can be used to find to sum the number from 1 to n. Okay. So we can write them 1, 2, 3, n minus 1, n, and then in below we can write them in reverse order, like n minus 1, n minus 2, and 2, 1, like this, and then we can sum them. Okay. So it will. There are how many pairs? There are n pairs. Yeah, n pairs. Okay. N terms, each of which is equals to n plus 1. Okay, and because we are summing them 2 times, okay, because we are summing them 2 times, so what happening? We need to divide this product n into n plus 1 by 2. So the sum of the natural number from 1 to n will be n times n plus 1 over 2. So this was the thing, or this was a technique which is useful to find the sum of first n natural number. Okay, and later in the beginning of 80, I think in 1801 somewhere, or so, after submission of his thesis, he submitted his. What is happening? He submitted his thesis in 1799. 1799, he submitted his thesis. And in 1801 somewhere, he wrote some he wrote something in Disquisitiones Arithmeticae, and it was submitted as a memoir. Memoir is that when you are learning something, where you are studying something, and you are extracting the knowledge from it, and then you are writing them. Okay, like this. So he, after the summation of thesis, and in 1799, in 1801, he submitted his Disquisitiones Arithmeticae as a memoir to the French Academy of the previous years. Okay, and then it was rejected from there. Even the work had been as worthless as the referee believed. Okay, so the referee was not in the mood to accept that one, so they rejected. Just like we do some research, and if they don't found it suitable, or if they think this is not good, so they reject. So this the same thing this French Academy did. So what happened? But that contains the theory of congruences, and later in somewhere after maybe 100 years or so, when the theory of congruences came into existence, so it was found that the same thing he submitted to French Academy, which was rejected by them. And then French Academy came to rescue, and they said that oh, it was either never submitted or there was something error or something. It was not exhaustible or something. They gave so many silly reasons. That was their stand. But thing is that the Gauss was, in fact, sometimes mathematician says that Gauss is the greatest mathematician. Okay, but of course we cannot say like this. Who is the greatest because there is no parameter. Anyway, on being asked who was the great mathematician in Germany, then Laplace answered that Pfaff was also mathematician. When the question indicated that he would have thought of Gauss was, then Laplace replied, Pfaff is far the greatest in Germany, but Gauss is the greatest in all Europe. So this was the thought of Laplace. So many times it happened. The similar thing was happened with this what is name? Descartes. Yeah, Descartes. You know the Cartesian coordinate system. The similar thing happened to him also. He was he was doing his PhD, and when he wrote the concept, even he at that time he wrote some definition of set, and then his supervisor was not agreeing with him. So there was a conflict between these two. Anyway, but finally he submitted his thesis. He got doctorate degree, and then he went to interview in the same university where his boss, that is his supervisor, was there. So because he was not agreeing with the definition of set, so what he has given, the Descartes has given, so finally he was rejected. He was not offered a post of a lecturer in that university. So this was the situation at that time. But later on, and also this Cartesian coordinate system was there in his thesis, and it was, but it was not much publicized. And it was publicized later on, and then now we know that what is a Cartesian system, and Cartesian coordinate system comes after the name of Descartes. So many times it happened. It is not like that if the person in front of you is not able to recognize your work, it doesn't mean that it is worthless. It is worthful. It may be more worthful for who is interested in it. And then Gauss sometimes he insisted that mathematics is the queen of science and the theory of number is the queen of mathematics. He was very much, although Gauss was working in so many fields of mathematics, in fact, all field of mathematics, whatever was the major field at that time. But he was much interested in a number theory in arithmetic. So this is statement of his shows this or established this, that he was much interested in number theory. Okay, so this was some history on letter. Let us see what is the definition of congruence modulo n. So this is another way of comparing the number. Okay. So let n be any fixed positive integer. You should know that this is a fixed positive integer, and A and B. We say that A and B are said to be congruent modulo n, and in symbol we use to write like this. If n divides the difference, that is n divides A minus B. And when n divides A minus B, it means we can write A minus B as A minus B equals to K times n. Okay, this is K times n, where K is some integer. And if you know that if A minus B divide n divides A minus B, then certainly B is also going to divide, n is also going to divide B minus A. is, if A divides B minus A, n divides A minus B, then this implies that n also divides B minus A. So if we say that A is congruent to B modulo n, then we can also say that B is congruent to A modulo n, or we can write like this: B is congruent to A modulo n. Fine. Okay. So let us move further. Okay. So if if n divides A minus B, this is the definition. If n divides A minus B, then we say that A is congruent to B modulo n. When n doesn't divide A minus B, we say that A is incongruent to B modulo n. Okay, and for example, we can take like 25 is incongruent to 12 modulo 7, like this. Okay, so when B is congruent to A modulo n, or A is congruent to B modulo n, we write like this. And if they are incongruent, we used to write A is incongruent to B modulo n. That is, n doesn't divide A minus B. Okay. Other examples, you can take 3 is congruent to 24 modulo 7. Minus 31 is congruent to 11 modulo 7. And minus 15 is congruent to minus 64 modulo 7. So these are certain examples. So A and B, whatever, maybe any integer, they may be positive or negative. Both may be positive, or both may be negative, or either of them, one of them may be positive, another may be negative. Okay. So there is no restrictions on them. Okay. So this now we have now seen that how we can write what is the definition of A is congruent to B, and certain example. Let us observe something. That is, first thing is that any two integers are always congruent modulo n, because if you are taking any two integers and we are subtracting them and divide, they are their difference are going to be an integer, and it is going to certainly divided by 1. So any two integers are congruent modulo 1. Okay, are congruent modulo 1. So you are taking any two integers. So A is always congruent to B modulo 1, like this. Whatever be the integer, A and B, maybe. Okay. And the second point is that two integers are congruent modulo 2 when both are even. That is when the difference of A and B is 2, so that their difference is always divided by 2. Either they are odd or they are always even. Both are even. Okay. So two integers are congruent modulo 2 when both are even or both odd. Okay. Okay, let us see the division algorithm for a given for a given integer a, we can write using the division algorithm. Division algorithm. Division algorithm as a equals to q times n plus r, where r is the remainder and q is the quotient, and a is divided by n. So this a we are choosing that a is greater than n. Okay, this is obvious thing we need to assume. So r is greater than or equals to 0 and less than, strictly less than n. So then a minus r is equals to q times of n, or a is congruent to r modulo n. A is congruent to r modulo n. And what is this r? R is greater than or equals to 0 and less than, strictly less than n. Okay. So, and r is some integer. So here a is congruent to r modulo n, and r can take values 0, 1, 2, up to n minus 1. Okay, so there are n possibilities for r. Okay, because there are n choices. There are n choices for r, namely 0, 1, 2, up to n minus 1. We see that every integer is congruent modulo n to exactly one of the values 0, 1, 2, 3, and up to n minus 1. Okay, so when you are dividing any number which is greater than n by n, you are certainly going to get a some remainder. It may be 0, 1, 2, but it will be fixed always in case of fixed a and n. So the number is the chosen number, like here in our case, a is going to be congruent to exactly one of 0, 1, 2, 3, or n minus 1. So essentially, that number can be equated to these one of these number. Okay, we don't be having more than these numbers. Okay, and this we have if you remember, these were kept. Uh, these were the elements of the group Zn. Do you remember? So Zn contains the remainder when the number is divided by n. Okay. Okay. So next, there is a theorem. This theorem says, next theorem. For arbitrary integers a and b, a is congruent to b modulo n if and only if a and b leave the same remainder the same non-negative remainder. Okay, same remainder, non-negative. Okay, non-negative remainder when divided by n. Of course, when we talk about the remainder, it is understood that the remainders are always non-negative. That is, they are greater than or equals to 0, always. Okay. So the from here, once we write A is congruent to B modulo n, A is congruent to B modulo n. The theorem says that when you are dividing A by n, you will be getting the same remainder, non-negative remainder, as when you are dividing B by n. Fine. Like in case here, here, if you see in this example, of course, 3 is less than 7. So we cannot divide. So remainder is 3. You can take. And when 24 is divided by 7, so it will, okay, 7 to 3 is 21. So remainder will be 3. All right. Like this. Okay. Uh, so let us see further. What is, let us prove this. Let us assume that A is congruent to B modulo n. So we need to prove that when we are dividing A and B by n, we are getting the same remainder. Okay. So A minus B equals to K times n for some K belongs to Z. K belongs to Z. Let B leaves remainder R. Remainder R when divided by n. Divided by n. That is B equals to Q times n plus R. So we are dividing B by n, quotient is Q and remainder is R. So certainly R is going to greater than or equals to 0 and less than n. And therefore, from here, okay, also A minus B also, since A minus B is equals to K times n, this implies that A equals to B plus K times n. Okay. And this implies that A equals to value of B, you can substitute from here. So we have a B, sorry, we have Qn, we have Q times n plus K times n, and anything else? Of course, R. So we can take n common. In the bracket, we are left with Q and K. Q plus K plus R. Okay. So what we have, A equals to n times Q plus K plus R. K plus R. So what we are seeing here, when A is divided by n, now quotient becomes this. Quotient becomes this. And this is the remainder. And this remainder is greater than or equals to 0 and less than n. Okay. So A also leaves the same remainder, remainder R when divided by n. Next we need to, okay, this is if and only if. Okay, so we need to, now we assume that A and B leaves the same remainder, and then we need to prove that A is congruent to B modulo n. Okay, conversely, suppose now we need to assume that A and B leaves the same remainder when divided by n. So A is equals to Q1 times m plus r, n plus r, and B equals to Q times n plus r, where r is between greater than or equals to 0, less than n. Okay, that is A and B leave the same remainder when divided by n. Okay. Now then, from these two, we can subtract them side by side. So A minus B, we can write A minus B equals to, in the right hand side, we have Q1n plus R and minus Q2n plus R. R gets cancelled. So Q1 minus Q2 times n. Q1 minus Q2 times n. So this implies that n divides A minus B. And by definition of congruence, therefore, A is congruent to B modulo n. And this completes the proof. For example, we can take example this minus, for example, minus 56 is equals to, we can write 7 times 9 plus r. Okay, 7 times 9 plus r. R is R will be here 7, I think. Okay, let us write 7. Yeah. This is 56. So here should be 9, because we want non-negative remainder. Okay, we want non-negative remainder. And 11, negative 11 is equals to minus 2 times 9 plus 7. So they both, when they are divided by 9, minus 56 and minus 11, they are leaving remainder 7 in each case. Okay. So minus 56 is congruent to 11 modulo 7. And also in case minus 31 is congruent to 11 modulo 7. Okay. In both the case also, when you are writing, okay, if you are considering this, so we can write 31 is equals to minus 5. In the very first stage, you may find that sir, how come we can divide 31? It is not divisible by any number completely. But we are not depending on whether it is even or whether it is odd. Okay, whether it is negative or positive. So when we are dividing it by 7, we can write it by negative 5 times 7 and plus 4. And similarly, 11 we can write 11 equals to 1 times 7 plus 4. So they both are leaving the same remainder. Okay, so this is one other property which comes as a result of the definition from the definition. Okay. Sometimes this theorem also used as a definition for congruence. In some author used to write this as a definition, and the one we have used here in definition, they write as it as a theorem. Okay. So we have another set of result. I mean properties, some properties of congruences. So next theorem. Next theorem is let n is greater than 1 be a fixed uh, integer and a, b, c, d are arbitrary integers. Okay, belongs to Z. Then the following properties hold. What are they? First, A is congruent to itself. A is congruent to A modulo n. The second one is if A is congruent to B modulo n, then this implies that B is congruent to A modulo n. And conversely, this also implies, okay. If B is congruent to A modulo n, then it implies that A is also congruent to B modulo n. Then the third one is, third property is, this is called transitivity. This is called reflexive. This is called symmetry. The second one. The third one is called transitivity. So A is congruent to B modulo n, and B is congruent to C modulo n. Then this implies that A is congruent to C modulo n. And the fourth one is A is congruent to B modulo n, and C is congruent to D modulo n. Then this implies that A plus C is congruent to B plus D modulo n, and we can multiply and add them side by side. So we are multiplying A times C, and in the right hand side B times D. Okay. So A is congruent to C. A is times C is congruent to B times C modulo n. And then fifth is A is congruent to B modulo n. A is congruent to B modulo n. Then this implies that A to the power k is congruent to B to the power k modulo n for any integer k belongs to Z plus. We are talking about the positive integers. Okay. So these are the properties. These are certain properties, and not only this. I think there are some more properties. We have there is one more property. I think. Let me recall. Okay, I think we can add or cancel something. Okay, let us see. Then the sixth property is that just hold on. Okay, if A is congruent to B modulo n, this implies that A plus C is congruent to B plus C modulo n, this one, and uh, one more thing, that A times C is congruent to B times C modulo n. So these are the properties of congruence relation.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.